In this section, we are going to describe the various shapes of the atomic orbitals and how you can visualize these orbitals in various types of atoms. The S-type orbitals are spherically symmetrical, and so the 1s orbital can be described as an ever-increasingly diffuse sphere as you go away from the nucleus. Oftentimes we will represent this shape using a probability contour, and as we have shown here. So in fact, you can never be 100% sure where the electron is going to be located. The 2s orbital is also spherically symmetrical. However, there is a slight difference between the 1s and 2s orbitals in that there is a high probability of finding electron density relatively close to the nucleus, and then a drop off in the probability as you get farther away, but then it becomes a high probability again. This roughly corresponds to the shells associated with the Bohr model. We say that in the 2s orbital, the region where there's this drop-off in the probability is represented as a node region of no amplitude in the particle wave. Shown here is a three-dimensional representation of the 1s orbital. You'll notice that in the cutaway you see that the intensity of the purple color is decreasing as you get away from the nucleus. The outside of this sphere is representing the 99% probability level. The similar plot for the 2s orbital is showing the node, and of course all s orbitals are spherically symmetrical. There are 3 p orbitals, and the psi-squared wave functions for the p orbitals in the second shell are shown here. In essence, they have 2 lobes. Each individual orbital has 2 lobes. And the directionality associated with this dumbbell shape is pointed along the axes of a Cartesian coordinate system. So the orbital on the left has the lobes pointed along the x-axis. This is referred to as the p subscript x orbital. The middle orbital is with the lobes along the y-axis. This is the py. And the orbital on the right is the pz. These correspond to the m sub l values of -1, 0, and +1. This slide shows you the 5 d orbitals that are possible in the n equals 3 shell. In this case, the d orbitals look sort of like clover leaves, 4-leaf clovers. The orientation with respect to the Cartesian coordinate systems are shown here, and so the corresponding m sub l values for the dxy, xz, yz, x squared minus y squared, and z squared would be -2, -1, 0, +1, and +2. Of course, the complexity of the orbitals increases as the L value increases, and you should be familiar with the shapes of the s, p, and d orbitals just to be aware of what the f orbitals are like, I'm not going to hold you responsible for these shapes, but the nodes associated with the orbitals increases, and so in this case there are 7 of the f-type orbitals, 2 of which are shown here. And these correspond to the m sub l values of -3 through +3. Likewise, I'm not going to require that you know the shapes of the g orbitals. This would correspond to the L equals 4, and there will be a total of 9 of these m sub l possible values. There is, in fact, no stable element with ground states that have g-type orbitals. So, but it is possible to have excited states that involve the g orbitals. It turns out that the particle waves associated with these wave functions actually have phase associated with them. And so you can sort of think of the s orbital as a standing wave that has a positive phase associated with it, whereas the p orbital is a standing wave that has both a positive and a negative phase associated with it. So, in essence, we have to take into account these phase designations when we talk about bonding, and so this will become important when we discuss molecules and how they go about interacting the waves of one atom with the waves of another atom. So here we have the 1s orbital, and compared to the three-dimensional shape of a p orbital, the positives and negatives representing the phase. We will see this again is very important, having to do with bonding.